the three big universities, and it's called as the Urban Research Intensive University. So we had a Nobel laureate in our department. He passed away in 2002, not in our department, in our university. He passed away in 2002, John Fenn. And the university is quite old. It was established in 1838, and we have about 30,000 students, 14,500 employees, and an operating budget of about $5 billion. And endowment is like in the US. This is like the money you sit on that comes from philanthropy or the profit you make. So that's your assets, basically. So what all that means, it's one of the serious research intensive universities. You might have not heard of it, but yeah, it is any serious research you think of, it happens in VCU. So that is VCU. So it also houses 36 research centers, and in terms of VCU programs, so it is number 1 in fine arts sculptures, and then it is 18th in nuclear engineering. So it's in health also, it's quite well ranked, health programs, and nuclear engineering. That is my part of my department. So nuclear engineering, which is mechanical and nuclear engineering, make up the department. So and of course this is the top image here is the medical campus, and it's downtown. If you go 1 mile or 1.5 kilometers up to the north, you see Monroe campus. Sorry, this is the Monroe campus. And just at the edge of Monroe campus is the College of Engineering. So this is right in downtown area. So we don't have, a lot of US universities have a dedicated campus just like this one, huge campuses, and there some of them, even though they are in urban, they have huge campuses like Georgia Tech, but ours is a urban university where buildings are scattered all over the city. So the department statistics are here. So if you are in, we advertise our programs. We look for good MS students, so and PhD students as well. So if you are interested in doing your education in the US, we are one of an attractive university just because the location, the high-ranked programs, and the type of research that occurs in the university. And also the location is important because Richmond is the capital of Virginia. It's 1 hour 45 minutes down south of Washington, D.C. So the university is well connected to the lot of Department of Defense or Department of other federal departments. So our students are they find jobs in all these federal government departments and labs and funding agencies. And one of the other thing that most people from Richmond are proud or not so proud recently is because of the data centers, large data centers from all big companies like Facebook, Google, all of them go through Richmond. So because Richmond is at the edge of US connecting Atlantic, and this is the Atlantic Ocean, and here is Europe. So most of the data from US connecting US to the rest of the world goes through this point here in Richmond here. And So people say 70% of the world's internet flows through Virginia. So because of that, there are so many data centers. And earlier, people welcomed them because they're source of jobs. But now there are so many, they have made the electricity bill go up, and the real estate is a problem, and they also need a lot of cooling because data centers take a lot of power, so a lot of water resources are diverted, and because these companies have a lot of capital, they are willing to pay, making the price of utilities like water, energy, and real estate very high. That now they're not liking. If there is any new data center coming up, people protest and they stop them uh, starting in Richmond. So that's the situation. Um, so, and again, big companies, manufacturing companies are also there. So the job, uh, our graduates find jobs immediately. So this is the Lego group is coming to Virginia, Richmond, and that is the main hub for most of the US. And also Richmond was the capital of tobacco in 19th and 20th century. So most of the cigarettes in terms of revenue came through Richmond area. So Richmond has a history of tobacco industries, and now it's all gone because the smoking has come down significantly, which is a good thing. They tried to fund our university. I mean, we had a good relationship with these tobacco companies, but then now even if they come and try to fund us, we say no to them because of the reputation of the tobacco. So that's about me and where I come from. So just, I did not know how many people will be attending today. So there is quite a lot of you, and if we go too much, we may just finish this class with your introduction. Just we'll go from here. Just your name, your education background, and just have you taken any materials class before. We'll start with, have you taken any materials class? Okay. BE or MS, MS, BTech or MTech? BTech, okay. And have you taken materials class before? Yeah, you should have done BE. Yeah, okay. And next, please. Perfect. Next. Okay, please. Okay, next. Okay. Okay. Okay, good. Next. Okay. Yeah. Okay. Thank you. Yeah.
I'm doing MS by research here in IIT Dharwad. So I have previously done material science, and I'm also working into body printing as well as polymer printing.
Okay. And I'm doing it. This is also good for you because you know one another now. So, yeah. Yeah. So, we'll go with Dr. Yeah. Right. Thank you. Okay. Perfect.
Good morning, sir. My name is Karthik, and I'm doing my final year BSc and
And you're taken material science. Okay. I think, yeah. Okay. Perfect. So, okay. Okay. Perfect. Okay. Next. Yeah. You don't have to get up because that will delay a little. So stay. Yeah. Sit and, yeah. Sit and just say, okay. Perfect. Yeah. Next, please.
from Bangalore. From Chanakya University, pursuing BTech second year.
Okay. Next. Okay. Yeah. Go ahead. Okay. Yeah. Okay. Next, please. Okay. Yeah. Next. Next, Prashant. Okay. Okay. Thank you. Next. Yeah.
Good afternoon, sir. Myself, Ganesh Mahari. I completed the ITI and ATS, and now currently I'm working in SDM Hospital as a part of the biomedical.
Okay. Good. Next, please. Yeah. Perfect. Next, please. Okay. Thank you. Next. Okay. Thanks. Next, please. Okay. Thank you. Next, please. Okay. Thank you. Next, please. Okay. Perfect. Thank you. Okay. Thank you. Next, please. Okay. And material, have you taken any material science? No. Okay. Who's next? Yeah. Okay. 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 So I see a good mixture of some people working in the Center of Functional Materials, some people having bachelors in metallurgy, and some people are doing research in composites and so on and so forth. So I think I'll I will still cover very little of basic fundamentals of materials, but I'll rush through that. And then we look at spatial or different cases of functional materials. So, um, why is it not moving? Okay, so have you shared this with them, Samshikra?
Clearly, but I think small changes can.
Okay, yeah. This is a rough schedule that what you have. Okay, so I'll be teaching in the morning and in the afternoon, 1.5 hours each, so 3 hours. You have demos later in the evening, and then you have demos in from 11:30 as well. And this is a rough uh, sketch of the schedule that you will have. And here is, again, there is small change in the syllabus too. So as I said, so I will, in my, maybe not this class, but in the next class, I'll quickly brush through some of the important concepts in material science which you need to understand in order to really exploit functional materials. Okay, so those ones like crystal structure, morphology, defects, and so on and so forth, I'll cover those concepts, and then I will switch to specific kind of functional material, which is magnetic materials. That is what I have expertise in. So magnetic materials, I will go through this chapter probably more thoroughly than the other ones. I might end up spending more time there. And then I also have some background in ferroelectric materials. We'll talk about that as well, how these are really the materials that can be used for various applications and have a lot of uses in day-to-day life too. And then, so this is all bulk materials, okay? So the concepts that you know, so for, I mean, in your fundamental materials class, will apply to all these, the magnetic materials, ferroelectric materials, which are the functional materials, right? I haven't, I'm not covering thermal materials or optical materials. That will prolong the course too much. But if you understand these, you get an idea how the functional materials can be used, or what parameters to look for in order to use them, or in order to manufacture them using additive manufacturing or even traditional processing. So that's all bulk materials. And then I switch to nanomaterials here, okay? Fabrication of nanostructured functional materials. And here, whatever you have studied here might be not directly useful, but some of the fundamentals will not change. So a lot of other things we will have to consider here. So we look at things like how to deposit thin films and where are thin films usually used. And how many of you have worked with nanomaterials? What kind of nanomaterials have you? Nanoparticles or nanoparticles? Transition metal oxide nanoparticles. Okay, so that's a good example of a nanomaterial. Um, there are thin films which are the thickness of these films are from 1 nanometer all the way up to 1 micron. You can say 0.5 micron is also a nanomaterial, but it's 500 nanometer nanomaterial, right? So we'll cover how to fabricate thin films and how their properties will be different compared to the bulk materials, and how they are useful. And then we'll look at nanoparticles after thin films. And then we'll look at how to do additive manufacturing of functional materials. So we need to learn this so that you get an idea, because when you do nanomaterial fabrication, it's a kind of additive manufacturing. You will see the similarities. Okay, um, so we'll look at additive manufacturing of functional materials, mainly focusing on the bulk here, and then we'll look at specific applications using ferroelectric materials or magnetic materials. In these applications, I'll be talking about magnetocaloric materials. These are a special case kind of magnetic materials. When you apply magnetic field on them, their temperature changes, and it's a reversible effect. You apply magnetic field, it heats up, and you take off magnetic field, it cools down, right? How we can exploit that for cooling purposes and have it is more efficient than the traditional vapor cycle refrigeration. And also we'll look at brain phantoms, which is a replica of brain, not just mimicking the structure, but also mimicking electrical and magnetic properties. And we'll see how we can use additive manufacturing to make these brain phantoms, which is quite challenging, and it had not been done so far. We were the first people to do these brain phantoms that mimic the exact structure, and we can structure and the functional properties, which is electrical, magnetic, and viscoelastic properties as well. So now we can have a brain replica that mimics somebody's brain structure and somebody's brain's electrical, magnetic, and viscoelastic properties. Meaning you can do experiments on this brain replica rather than giving them certain procedures. You can test the safety and effect of using different treatment procedures. So I'll talk about some of the brain treatment procedures before going on to the brain phantoms, so you get an idea why we need brain phantoms. And then I'll talk about the transcranial magnetic coils. Again, these are the coils which are basically copper windings to which we supply a large current, so they generate a magnetic field. And that magnetic field, when you put on top of a person's head, will induce an electric field in the neurons. And when you induce electric field in the neurons, you can stop the neurons communicating their signal, or you can make them communicate a signal. So that means you can make neurons active or neurons or suppress neurons. And if you do that, you can actually control specific part of the body. So I'll be talking about these exciting techniques, exciting properties of the materials, and touch upon how you can use these materials in additive manufacturing to solve some of the challenging problems. Okay? So again, so there is a small here, I'll combine both of them here, and I'll bring a second case study here of brain phantom and TMS coils. Okay, so in the last 3 slides, there will be a slight modification because I realized that, and also Professor Somshekhar, I will be talking a lot on additive manufacturing, so you don't need to know the basics here. So what I'll do is I'll merge this with the functional material additive manufacturing and do the case studies more. So we'll talk about brain phantom additive manufacturing and TMS coils additive manufacturing. Okay. And here are some of the reference books. You don't have to purchase them, but if you can get them from library or e-library or somewhere, you can get an electronic copy. That will be really helpful. And the Material Science and Engineering and Introduction by Callister, it's a Bible for material science. Everywhere you go in the world, people refer that. How many are familiar with Callister? Yeah, okay. So it's a well-referenced book. And for magnetic materials, although Callister covers a lot of it, but I suggest if you get a chance to read Introduction to Magnetism and Magnetic Materials by David Giles, that will give you in-depth understanding. David Giles is my PhD advisor, and this book is also quite widely used. And then for magnetocaloric additive manufacturing of magnetocaloric regenerators or magnetocaloric materials itself, there is a book by Andrei Kitanowski. That is another book that you can refer apart from the slides that I present here. And then for ferroelectric materials and energy applications, Hong and Scott is another great book. And again, I think for additive manufacturing book, I suggest you follow Professor Somshekara's reference book that he suggests. Okay, so these are the reference books that I'll be referring to. So now let's come to material science. And I'm sure you already heard from the head of the department who also said that, if you want to increase the efficiency or any problem can be solved, or the limitation to improve anything, when you reach the extreme performance. This is the same experience I had when I was doing my BE. I remember I was learning energy conversion engineering or IC engines. We were looking at different IC engines. And again, I don't remember everything now, but the diesel engine we were looking at. And one of the biggest issues for efficiency was the pressure. When you compress the gas mixture, you could only compress to a certain pressure, beyond which the materials can damage. But if you compress for higher pressure, you get higher HP, and hence you can have higher efficiency. And any thing you change in the cycle, in the structure, in the geometry, all that would only give you 0.1 or 0.5% increase in the efficiency. But if you change the Young's modulus or Young's modulus of the material by just a small amount, you would increase the efficiency by 2, 3, or 5%, which should be significant for an IC engine. So this was my undergraduate experience as well, and I was really impressed by what material science can do, and that is the case even today. So whenever you are stuck to a certain efficiency, for example, solar cells, right? I'm sure you are familiar with the rooftop solar cells. They are so expensive because you need a larger area to generate certain watt of power. For example, if you want to run 2 fans, 5 lights, and a small heater, you need 10 meter by 10 meter PV panels, right? Photovoltaic panels. Because their efficiency, these are silicon wafers, their efficiency is about 12 to 15%. But if you increase 12 to 15% to 20%, you don't need the same amount of energy you can produce by reducing almost half of the surface area, and that would reduce the cost significantly, right? So these are some of the examples that what materials science can do. And even the example I also gave about completely revolutionizing things like the batteries, right? So earlier batteries we knew were lead acid batteries, right? The big where you had to store lead, and now the lithium ion batteries came. So now all our uh, computers and smartphones run on lithium ion batteries, and they have revolutionized how we carry our electronic devices. So the lithium ion, does anybody know who is the person who was, I wouldn't say who invented lithium ion battery, but who played a significant role? He got Nobel Prize. Goodyear, John Goodyear, from University of Texas, Austin. He recently passed away. He got Nobel Prize when he was 95. And he said, I don't need it now. So anyway, but likewise, the other thing about, I mean, another example is, again, with the mobile phones, the kind of audio they play, right? Earlier, do you remember the really old mobile phones, the kind of sound you used to get? Annoying sound. Even when it rang, it was like, you better answer it, right? Now, you can really play a nice tune. It can play all the frequencies, right? So any note in the music, your phone can play, right? Though the speakers have become so good. Why do you think that is? How do you think the speakers have become so good? Of course, it's culmination of so many other technologies, but one technology played a big role. Can anybody tell me why, how your phones have become so, have so good speakers? Good materials. Yeah, that's, yes, of course, that's the theme of the class. But can you tell me what materials in a speaker? Sorry? Yeah, that's exactly right. Neodymium iron boron magnets. Earlier, speakers had cobalt ferrite or iron, some ferrite, hard ferrites. These were the iron-based magnets, which were, you might have seen, dark, big magnets. They're still used in refrigerator magnets now. They're inexpensive, but they're not as strong. But the new rare earth magnets, that is neodymium iron boron magnets, they are so powerful that a small magnet can vibrate your membrane of the speaker, and it can respond to any small current, right? A small signal that comes out of a microphone due to any variation in your speech can change the current, and that small current can make the magnet vibrate the membrane of the speaker, and you get that. And that's how you're able to hear clean music and have it everywhere you go. And that's because of neodymium iron boron magnet. And neodymium iron boron magnet also has revolutionized not just the speakers, but also the electric cars. Okay, they run on motors, right? Electric cars can't use IC engines, they have to have motors. These are permanent magnet motors. And the permanent magnet, which one do you think they're using right now? They can't use the ferrites, which are bulky and not as powerful. So we'll talk about the energy product of a permanent magnet, how to measure the strength of a magnet. So these are some of the examples. So When I graduated, I was of the opinion that materials science can really uh, solve a lot of problems, and that is true even today. I still hold the same opinion. If you really understand material science very well, and if you really dig into the periodic table, you have solution for everything. I stand by that statement. And you just need to look really deep into the periodic table. Okay, so that's with that. That's my case. With that, I will. I thought. Sorry, this is a older version of my slide. I had two other slides before this, which wherein I showed like there are grand challenges for the entire. I mean, in the if you look at different governments, they come up with grand challenges, what the people are facing, such as clean water, affordable energy, affordable food, good health system, communication, right? These are all basics of any society. And some of the grand challenges are these good water. And if you see all these grand challenges, there are about 10 grand challenges. And if you see all these 10 grand challenges, and you can clearly see in all of them, the biggest improvement you can make is through new materials. And let me see, I thought I had a, oh yeah, I have it at a later stage. Okay, so what I will do is I'll not go through I'll explain to you how materials, what are the basic pillars of material science. Probably some of you are already familiar. I'll talk about this a little later, but before that, yeah, these are the grand challenges that I was talking about. So this is the National Academy of Engineers, that's American Academy. But if you look at any government's grand challenges, there might be small variations, but typically these are the biggest problems that the society has to overcome, which is making solar energy economical, provide energy from fusion, which the director talked about from sun, because sun can give abundant energy. So that means we must be able to run a nuclear fusion reaction continuously, sustainably, to exploit the fusion energy. So for that, some of the biggest challenges are again in material science. Okay, how you control the fusion within this tokamak is a big nuclear fusion reactor, and controlling the fusion, the flume of the nuclear fusion is a big challenge. So um, one of the ways you can do that is by applying magnetic fields in certain way to contain that nuclear fusion plasma. Um, and material science has improved the way you can control it, but it's still not there yet. Okay, and then develop carbon sequestration methods, meaning carbon capture methods. And for that also you need new materials, how you can capture carbon. And for all these circles that I have drawn, these are all the problems that can be solved with new materials. Okay, so engineering best medicines. Medicines are nothing but new drugs, right? New chemical formulas, new materials. And reverse engineering the brain. That is You would not think you need new materials there, but I'll show you. Yeah, that's my part of research, how materials has helped me to reverse engineer some part of the brain or some function of the brain. Okay, and prevent nuclear terror. There also you need new material to detect any radiation, any nuclear material that's transported without appropriate licenses, and so on and so forth. These are all the grand challenges that can be solved with new materials or advances in materials. Okay, so again, sometimes we think that these are the challenges and we need to work towards it, and that we have to solve it. You have that dedication and energy to solve certain problems, which is the grand challenges, right? So, but sometimes new materials or the real breakthrough doesn't come from dedicated effort in solving certain problems. It comes by serendipity. The neodymium iron boron magnet, people, the US Department of Energy invested so much money to actually come up with new magnet. The earlier magnet was called samarium cobalt. Okay, so there was one transition metal and one rare earth metal. Combine it together, you get a nice uh, powerful magnet, samarium cobalt. So, but these both are really expensive materials. So, government of US Department of Energy invested a lot of money to come up with alternatives. So people were looking all from periodic table, all transition metals, all um, rare earth metals. After so many years, nobody came up with new material, but one lab, by serendipity, they something went wrong, and boron fell into iron and neodymium, and boom, that material was more powerful than any of the magnets we knew. So that's because it was not they were trying to solve the challenge, but they were just doing basic material science. They were just looking at different material behavior, and there came the solution. Likewise, so challenges, yes, you can tackle them, but if sometimes if you just like some fundamental science, you should pursue that passion too. You should not be just going after challenges to solve those challenges. That may not happen. Sometimes if you just do the science you like, you may come up with breakthrough. Okay, so challenges versus passion, because when I showed the grand challenges, I needed to talk about the passion as well. So we did not invent steel because we ran out of bronze, because somebody was testing something and steel seemed to be a better material, and probably nobody bought it before. But then when people started to see its hardness and its malleability, it was adopted. Likewise, we did not invent automobiles because we ran out of horses, but somebody was very interested in seeing how the fuel burns and how the pressure expands, right? Um, and similarly, we're not going to space because we are running out of resources on Earth. We are going to space because we are natural, curious people and we want to explore. So that is passion versus challenge. So pursue your passion as well, although there are grand challenges. But if you pursue your passion, um, sometimes you may end up solving the grand challenges. So, and these are some of the examples of of materials that have a lot of promises or opportunities. So for example, functional materials that I talked about: electric, magnetic, optical, and thermal. So these can be exploited in many applications. These can solve many challenges. And then there are other materials called 2D materials, graphene, and there are many other monolayer materials, new materials, and then nanostructures, nanoparticles, nanotubes, nanowires, nanodiscs. There are all sort of nano structures. But in order to understand these or uh, fabricate these or come up with new kind of these materials, you need to understand the fabrication process. Okay, we'll go through how these materials are made, the nanostructures, and that will give you some idea of additive manufacturing as well. So you will see some similarities between the fabrication processes of nanostructures and additive manufacturing processes as well. And then there are other materials called biomaterials, scaffold. So these are the biomaterials which, for example, scaffolds or hydrogels, some polymers, and even conductors, um, such as titanium. Some forms of titaniums are conductors. Um, so these um, are all biomaterials. They're used for scaffolds, meaning to make if nowadays bio 3D printing is an upcoming field. So they can make blood vessels. And to make these blood vessels, you have to first have a scaffold. And scaffold materials are some polymers. Okay, these are hydrogel polymers. And those, without those new polymer materials or hydrogel materials, you can't make these scaffolds, which means you can't make blood vessels, artificial blood vessels that can go back in your body. Okay, and other biocompatible polymers that, for example, some of the stents can be polymers and some are titanium based stents. So there are many examples. These are biomaterials. And then there are some materials that are very critical, meaning we don't have a lot of these materials on the Earth's crust. Okay, so these are critical materials. Does anybody know which are examples of some critical materials? They are very, the quantity of these materials on Earth crust is very low. So if mining them is problematic. Cobalt is a critical material. Sorry, which one? Lithium is also, it is not considered as critical material, but it is also one of the rare material, or the supply chain can be disrupted. Um, Indium is another critical material. And then a lot of the rare earths are critical materials. For example, samarium, terbium, dysprosium, these are all needed for magnets, and those are critical materials. So you have to recycle them, otherwise you will lose them. And once you lose them, you don't have any of those materials. And if you don't have these materials, for example, indium plays a critical role in photovoltaic cells. And if you don't have indium, then you can't have solar cells. Although it's very tiny amount that is put in, but you need indium, and you need cobalt for many other applications. You need neodymium for, neodymium is not a critical material, but for these neodymium magnets, they add dysprosium and terbium. Those are critical materials. So you need to recycle these materials. Okay, then material design is another important concept we need to understand, because that can solve many problems. We don't have to do ethyl methyl chemistry. Has anybody heard of this term, ethyl methyl chemistry? So basically you put in two chemicals and see what happens, right? And that's what material science was before. People just took elements from each, from the periodic table and looked for different alloys and looked for new properties. So you don't have to do that, because that would take a long time, because the number of combinations you get in 118 elements is too many. You can actually do computation. You can determine whether two materials will combine to form a new material with better properties by computation. And nowadays, uh, machine learning can accelerate this a lot. Okay, so you can do computation before you go on to do ethyl methyl chemistry. Okay, so um, that's about the scope of material science, meaning how material science plays a big role in our day-to-day life. And with that, I just want to show some of the work that I do in my lab. I already talked a little, but I started with my PhD was in magnetocaloric materials. So I looked at magnetic materials, and I prepared the materials, characterized them. So again, with ethyl methyl chemistry, I did not do any computational studies to look at um, the resulting properties. But so this is one of the areas we still work on, and we do computation nowadays. We do additive manufacturing of this material. And then the other material is piezoelectric polymers. There is piezoelectric materials, which we'll talk about, but my lab specifically works on piezoelectric polymer, which is PVDF. It can be used as an energy harvesting material. And then I work on biomagnetic materials. So we make nanoparticles that can be used for cancer treatment, or these are also used as MRI contrast agents, and they can also be used for electromagnetic shielding, meaning your 5G, 6G signal, you can block it with this material. Okay, so that is electromagnetic shielding material. So you make a box out of this material and put your phone, signal will be cut off, right? So that kind of material. And we can select what frequency. Can we only block 5G, or can we only block 4G, and like that. So that's another area of my lab's research. And then last but not the least, this is the brain stimulation. And we use magnetic fields to stimulate brain. That is one of the most exciting part of my lab. Whenever I talk about this, students want to come and work in my lab when I talk to them about this research. This feels very sci-fi research, but underlying principle is just basic electromagnetism. Okay, so you will hear about all these 4 topics in some sense. And yeah, here is that's a rat's brain phantom. It has electrodes that can measure the stimulation strength. This is human brain phantom. This is a magnetic coil that you have to place on the brain to stimulate. And this is what I'm collaborating with Professor Somshekara's team to make these kind of coils, because these can't be fabricated with conventional machining. We tried, not that we directly came to him. We tried to make this, and it was a disaster. So we hope that with additive manufacturing, we'll be able to make such a complex shape of this functional, that is magnetic material. And 2 PhD students, actually, they are in Richmond, Virginia, who are PhD students from IIT Dharwad, Deepak and Vinayaka. They are working on this project, and I'm sure other team members are also contributing. So that's one uh, one of the research interests. And then the magnetocaloric materials I talked about, magnetic nanoparticles, and then we are also working in robotics. So we are trying to use robotics for additive manufacturing. Well, in a true sense, an additive manufacturing device or additive manufacturing machine is a robot in itself. Okay, so but we are trying to use collaborative robots with 3D printers so that we can automate manufacturing. So I think 1 o'clock. Right time, right? 1:03. So next class, I'll talk about these basic concepts. During the same time, I'll talk about what are smart materials and type of materials and fundamentals of material science. Okay? So with any questions? So yeah, I think I've been talking by myself. I think we have to avoid this kind of lecture. So raise your hands whenever you don't understand anything, or if you get a question that you think um, deserves an answer. Uh, there is no silly question. All questions are important. There can only be bad answer or a silly answer. Okay? All questions are important. So any questions now? No question. That means you understood everything or you understood nothing.
Next class, I'll ask.
Yeah. So there is a question here. Yeah.
How exactly you are mapping your cell?
The
Last slide you have shown that in the rack where you have.
yeah. So this one, right? So these are what we call as triaxial dipole probes. So these are embedded inside, and then it's a tricky procedure. We have to know which part of the brain they have to go, because that is determined by MRI images. We get the coordinates, we use those coordinates, and then place these probes, and this is all manual.
You are inserting inside or just
So when we make this brain phantom, we have shells, and before pouring on the polymer that is conductive, we have specific holders that we put them on the molds, and then place the probes, and then pour the conductive polymer, and then place another mold.
similar way you are using on the human cell?
Yes. So
Because they might have got the coordinates of exact.
yeah, we have to have the exact coordinates. You can't just place anywhere, right?
That single MRI uses that coordinates or you have to have a repeated MRI?
We take well, single MRI will have several slices, right? So one MRI is enough to know which location we can place this. So we take the MRI. First of all, to print this, it's printed from MRI images, right? So we take the MRIs and slice. We segment different regions: skin, skull, CSF, gray matter, white matter, and ventricles. And then all these have shells. And when we bring all of them together, then we know the coordinates where the probe has to go. So we place it before we bring them all together. So this is actually a DBS probe. DBS is deep brain stimulator. That's a surgically inserted probe that is that's a treatment, established treatment for treating Parkinson's disease. So if you get a chance today, go and Google DBS therapy, deep brain stimulation therapy. And these probes are surgically implanted in patient's brain, and the leads come out and are connected to a battery pack that is below the skin here. And as soon as that is turned on, Parkinson's patients have these tremors. They're always like that. And as soon as you turn on, they become like normal people. It sounds like science fiction, but that happens. VCU hospital does 2 such surgeries every week. So it's a complex surgery. I have attended a couple of those surgeries, and it's mind-blowing how, because they don't anesthetize, brain doesn't have pain sensors, so the person is awake and they're inserting these leads. So that's that. So it needs to have very high accuracy. So they're constantly doing CT scan while they're operating. Any other questions? Yeah. Mm-hmm. So there are other conducting polymers, but the one that we wanted to use, because we want big brain, right? I mean, you need a liters of these polymers. So we wanted inexpensive ones. The conductive polymers, PCMB, they are used in organic photovoltaic solar cells. Those are expensive. The ones we made ourselves, we took PDMS and added carbon nanotubes. And the more carbon nanotubes you add, the conductivity goes up. So we basically titrated for what loading percentage, what conductivity we get. And we have that nice graph, and we exactly know for this conductivity how much carbon nanotube we need to put. That's PDMS plus CNT composite. Yeah.
So again, the same, I will take this.
Yeah.
As soon as you add the carbon polymer, what is the expansion rate of as the conductivity increases, heat increases?
So there is, again, carbon nanotubes, when they go into this polymer, there is no expansion. But it becomes viscous, more viscous. Yeah, it doesn't expand in terms of volume. The volume remains, or maybe slight change in volume, but the volume doesn't change much, but it becomes more viscous. So it's hard for you to make the polymer flow through all nukes and crevices of the brain, because it's very complex, right? The folds are very complex. And what was your other question again? How? Expansion, there is no expansion. It
Only gets viscous.
viscous. And there was something about conducting and heating.
So once you add more and more nano, as this
Yeah.
is the rate of conduction.
Yeah. Sure. I mean, you mean the conductivity that is 0.33 Siemens per meter for gray matter, and so the CSF, that is cerebrospinal fluid, is more conductive. That's why we use saline solution for that, because it's thin material, right? So it's 1.3 Siemens per meter. And the skin's conductivity is less than 0.01 Siemens per meter. Yeah, so but once it cures, it becomes solid. Yeah, to begin with, its viscosity is low. Yes. Any other question? Yeah. Yeah, so PDMS is not conductive. Yeah, it's a insulating polymer, and we need a flexible polymer like PDMS so that it can go and form the shape of the brain. And it can also cure. And when it cures, it becomes like the PDMS has not exactly the same mechanical properties, but similar mechanical properties as GiAN. So that's why the flexible electronics use PDMS as one of the materials. So that's why we use PDMS as the base polymer. And there are other options, of course, and it's cheap too. So good. So you don't have to wait until the end. Whenever you have questions, you can raise your hand. I prefer to have an interactive class rather than just me talking one way. Uh, so just interrupt me and ask me a question, and I will try to answer to my best capacity. Okay, so you might be hungry now. So we'll have lunch.